Section 4.9, we're going to talk about antiderivatives. As you know, there are basically two types of people in this world, those who are for derivatives and those who are against derivatives. You really can't be ambivalent about derivatives. You got to take your stand. Either you're for them or you're against them. People who are for derivatives are called pro-derivative people. People who are against derivatives are called antiderivatives. Actually, that has nothing to do with what we're talking about. Here's what an antiderivative is. If we let f of x be a function, then what we're going to do is we're going to say that capital F of x is an antiderivative of f. An antiderivative of f if we take the derivative of big F and we get little f. Now notice that we said that it's going to be an antiderivative of f, not the antiderivative of f. And the reason for that is there's going to be many antiderivatives for any given particular function. Let's look at a very simple example. If we let, let's erase that. If we let f of x be 2x, well, can you think of a function, capital F, whose derivative is going to be 2x? Well, sure you can. If we let f of x, capital F of x, be x squared, so if that's the case, then what does f prime of x equal? Well, it equals 2x, which is, again, little f of x. Well, that's all fine and dandy, but as you know, if we let capital F of x be, say, x squared plus 3, then what happens if we take f prime of x? Well, we get 2x again, which is equal to little f of x. And so, since the derivative of a constant is 0, if you add a constant onto the end of any antiderivative, the derivative is going to be the same thing. So what we would say then is that we would say the most general antiderivative of the function f of x equals 2x is going to be capital F of x equals x squared plus any constant. So where c is any constant. And the reason for that again is that no matter what c is, if we take the derivative f prime, capital F prime, we get 2x plus 0, or just 2x, which is exactly what little f of x is. So that's the idea behind antiderivatives. You're looking for a function whose derivative is a given function. Now you should look over the table on page 329 and get familiar with those antiderivatives. The one you need to probably really concentrate on, the one you're going to use the most, is if we have f of x equals x to the n, then if we let capital F of x equal x to the n plus 1 over n plus 1, well, then that means that f of x, capital F of x, is an antiderivative of f. In other words, we're basically using that power rule for differentiation. The way you found derivatives using the power rule, we're using it in reverse. So remember, when you took the derivative, you brought the power down, reduced the power by 1. Well, here you're basically doing the opposite. You're increasing the power by 1 and dividing by that power. So, for example, if we wanted to find the most general antiderivative of little f of x equals 3x cubed plus 2x squared minus 5x plus 2. That's a cubed there. 3x cubed plus 2x squared minus 5x plus 2. Let's go ahead and let f of x be that most general antiderivative. And so we're going to use that power rule in reverse. The constants are going to stay put. So we'll have 3. That constant comes down. X to the cube, the antiderivative of that, we're going to increase the power by 1 and divide by that. So we add 1 to 3 to get 4, and then divide by 4. Same thing, we have 2x squared here, so we're going to increase the power by 1. So 2x to the 2 plus 1, which is 3, divided by 3, minus 5. Now remember, if we just have 5x, the power on that is 1. So you increase that by 1, and what do you get? You get x to the second, so you divide by that power. And then plus 2. Now what's the antiderivative of a constant? Well, the antiderivative of a constant, there's a couple ways you can think about it. Remember that if you took the derivative of a constant times a variable, the derivative was just the constant, because you're thinking of taking the derivative of a line, and the derivative, remember, gives you slope of the line tangent. Well, the line tangent to a line is going to be the line itself, so the derivative is going to be the slope. But another way to think about it is, say that if you just have a constant 2, you can think of that as 2 times x to the 0 power. And you can use this antiderivative rule for powers. So you're going to raise the power by 1. 0 plus 1 is 1. And so you're going to get plus 2 times x to the first over 1, or just 2x. And you think about it, if you went the other way, if you took the derivative of 2x, you would get just 2. Now, again, we wanted the most general antiderivative. There's infinitely many, because you can add any constant you want on the end, but to kind of generalize everything, we'll just add a constant c onto the end of that thing. And you can always check by seeing that if we take f prime, the derivative of capital F, we're going to get little f back by using the power rule. And so that's an example using that power rule. Again, you're going to want to look over those particular antiderivatives of particular functions in that table on page 329 and get familiar with those. And basically, you're just going in reverse order. Of course, since the derivative of e to the x is e to the x, that means the antiderivative of e to the x is also e to the x. So e stands for easy, as we have talked about. And the antiderivative of 1 over x, that's a good one to remember, is the natural log of the absolute value of x. And remember that, so let's go ahead and say that. If f of x equals 1 over x, then the antiderivative of that, the function whose derivative is 1 over x, is going to be, we'll call it capital F. It's the natural log of the absolute value of x. And remember, the reason we put the absolute value signs around the argument of the natural log there is because we can't take the log of 0 or a negative number. It doesn't make any sense. So I'll let you look at the rest of those functions on that chart on page 329. And it's a good idea, too, to actually memorize those antiderivatives. All right, let's go ahead and look at a few examples from your homework. If we look at something like, say, number 3, we have a function, little f of x, and it is equal to 5x to the 1/4 power minus 7x to the 3/4 power. We want to find the most general antiderivative of this function. And so the most general antiderivative, which we'll call capital F, we're going to use that power rule for antidifferentiation, which remember means we're going to, well, just bring the constant down. So we'll bring the 5 down, and we're going to have x to the 1/4 plus 1. So 1/4 plus 4/4 is 5/4, and then we're going to divide by 5/4 minus the constant 7 times x to the 3/4 power is our original function, so add 1 to that, add 4/4 to that, and get 7/4 divided by that same amount of 7/4. Now, we don't want to leave it like that. Of course, we need to tack on that plus c. This is very important, by the way, to add that plus c. You'll lose lots of points in Calc 2 if you forget that plus c, because this is really the basis for a lot of the problems that you're going to be doing in Calc 2, finding antiderivatives. So always remember to add that constant. But anyway, we want to simplify this, so we're going to multiply by the reciprocal here since we're dividing by fraction. So we'll have 4/5 times 5x to the 5/4 minus 4/7 times 7x to the 7/4 plus that constant c, and you can see we have 5's dividing to 1, 7's dividing to 1, not canceling, we don't say canceling, dividing to 1, so we get then 4x to the 5/4 minus 4x to the 7/4 plus any constant that you want c. Again, that c represents any constant because the derivative of a constant is 0, so this is the most general antiderivative of the original function f of x that was given to us. And you can always check your answer here. That's a nice thing about finding an antiderivative. You can check your answer by taking the derivative. If f prime, so you can check that if you take f prime, capital F prime, you get little f. That way we know we've had the right antiderivative. All right, let's go ahead and take a look at another problem. How about number 18, where we're actually given a second derivative. In number 18, we're told that f double prime of x is equal to the cosine of x. And from that, we want to find a possible function for f of x. So we have the second derivative. We want to work backwards to find f of x. So that means we're going to have to find two antiderivatives. So f prime of x is going to be the antiderivative of f double prime of x. Remember, the antiderivative of cosine from the chart there is sine of x, and that's just simply because the derivative of sine is cosine. Now, I'm going to have to add on a constant, so plus some constant c. So now we want to find the antiderivative of f prime of x to get f of x, which is what we were asked to find. Well, the antiderivative of sine is negative cosine. Since the derivative of cosine is negative sine, the antiderivative of sine is negative cosine. Plus, the antiderivative of a constant, as we talked about earlier, is the constant times the variable. So the antiderivative of c is c times x. And now we have to add on another constant. Let's go ahead and just call that d. So the most general form for the function f, whose second derivative will just simply be the cosine of x, is going to be this right here. F of x will be negative cosine x plus cx plus d. If you take two derivatives of that thing, you will get cosine of x. And we had to keep that general because we didn't have any values for f prime or f, which is not going to be the case in the next example that we're going to look at, which is number 28, where we are told that f double prime of t, in this case, our independent variable is t, is equal to 2 times e to the t plus 3 times the sine of t, but that's not all. We are given some more information. We're told that if we put 0 into our function f, we get 0 out. And if we put pi into f, we get 0 out. So f of pi is also 0. So let's go from there and see if we can find, again, we want to find f. In this case, it'll be f of t, since t is our variable. So we're going to first find the antiderivative of f double prime, which will give us f prime. So f prime of t is the antiderivative of f double prime. So the antiderivative of 2e to the t, that's just 2e to the t. And the antiderivative of 3 sine t is going to be, let's see, 3 times, the antiderivative of sine is a negative cosine. So let's just make this a minus 3 cosine of t plus some constant c. Now from that we want to find the antiderivative of f prime to get f. So f of t will be the antiderivative of f prime. Again, the antiderivative of 2e to the t is 2e to the t. Antiderivative of cosine is sine, so we'll have a minus 3 sine of t. Just bring that minus 3 down. That just stays with you. And then the antiderivative of c, some constant, is c times your variable, which in this case is t. And now you need to add on another antiderivative, which is d. Well, now here's where the other information comes in. We were told that f of 0 is equal to 0 and that f of pi is equal to 0. Well, let's go ahead and start with the fact that f of 0 is equal to 0. If we plug that into our function, f of 0, just putting it in for t, we get 2e to the 0 minus 3 sine of 0 plus c times 0 plus d. What this is going to do, since this has to come out to equal 0 according to the given information, is allow us to solve for d. So 2e to the 0, e to the 0 is 1, so that's just 2. Sine of 0, of course, is 0, so minus 3 times 0, which is 0, plus c times 0, any constant times 0 is 0. So we're basically left with 2 plus d equals 0, so d is negative 2. Alright, so now we've made a little bit of progress. We now know that f of t is 2e to the t minus 3 sine t plus ct minus 2. Again, because d is negative 2. We found that to be the case. Now we should be able to use the other piece of information, that f of pi is equal to 0, to find c. Let's see what we can do with that. So f of pi is equal to 2e to the pi minus 3 times the sine of pi plus c times pi minus 2. And that has to come out to be, what do we say? It has to come out to be 0. So we should be able to solve this for this equation right here, solve that for c, and that'll let us know what the other constant has to be. So 2e to the pi, we'll just leave that like that. Sine of pi, of course, is 0, so we get a minus 0 there, plus c times pi minus 2 equals 0. Solving for c, we can see that, well, let's see, c times pi is going to equal 2 minus 2e to the pi. So dividing both sides by pi, then, we get that c is equal to 2 over pi minus 2e to the pi over pi. So, putting all of that in, which is kind of ugly, but that's alright. We'll put all that in for the constant c. We're going to get our final form for our function f. F of t is going to be 2e to the t minus 3 sine t plus the quantity of 2 over pi minus 2e to the pi over pi times t minus 2. And there you have it. Took a little bit to get there, but that is our function f. Alright, let's go ahead and just look at one or two more examples, at least set them up. I want to look at number 40, just to make sure that we're clear about the interaction between acceleration, velocity, and position. We have acceleration a of t, and this problem is given by 5 plus 4t minus 2t squared. Now, before we do this problem, let's remind ourselves that if s of t is a position function. So that tells you the position of some object after t units of time, usually seconds. Then s prime of t, the derivative of the position function, is what we normally call v of t. It's the velocity function. So velocity is what we get when we take the derivative of the position, because again the derivative tells you how fast a function is changing, and how fast a position is changing is the velocity. Now if we take the second derivative of our position function, s double prime, that is to say the first derivative of our velocity function, v prime, that is the acceleration a of t. Acceleration, and that makes sense because what does acceleration tell you? It tells you how fast your velocity is changing. So the derivative of the velocity is the acceleration. So what we're going to be doing here basically is working backwards. We're going to be starting with acceleration, s double prime. From that we can get with an antiderivative s prime, which is the velocity, and from that we can get s prime, which is, or sorry, just s of t, rather, which is the position function. So now, looking back at what we were given in number 40, we're given that a of t, or the acceleration of a particle, is 5 plus 4t minus 2t squared. We have an initial velocity, so we're given an initial velocity v of 0, which is equal to 3 meters per second. And we're given also that its initial displacement, in other words, where it is at time t equals 0, is at 10 meters. So that's displaced 10 meters from position 0. We want to find its position after t seconds. In other words, what that means is we want to find our position function s of t. And the way we're going to do it again is we're going to take our velocity function here, a of t, acceleration function, and we're going to work backwards. We're going to take the antiderivative to find velocity, and then the antiderivative of that to find the position function using these initial values, v of 0 and s of 0, to get our constants. So let's go ahead and just see how that goes. So our velocity function v of t is going to be the antiderivative of our acceleration function. So remember, the antiderivative of a constant is just 5, well, it's the constant times the variable, so 5t, plus 4t squared over 2. Remember that the exponent on t here is 1, so raise the power by 1 and divide by that amount, minus 2t to the third over 3 plus some constant c. So let's go ahead and simplify that. That's equal to 5t plus just 4 over 2 is 2t squared minus 2/3 t cubed plus c. Now from the fact that v of 0 is equal to 3, we're going to be able to find c. If I put 0 in for t, I get 5 times 0 plus 2 times 0 squared minus 2/3 times 0 cubed plus c. That all has to come out to be 3. That tells me, of course, since all these go to 0, that c itself is equal to 3. So now I have my velocity function v of t, and it's equal to, replacing our c here with 3, we get, what do we get? 5t plus 2t squared minus 2/3 t cubed plus 3. So from there you can find the position function by just taking the antiderivative of that, and again using the fact that s of 0 is 10 to find the constant for that antiderivative. So I'll leave that to you. Alright, I'm not going to do anything with 41, but I do want to point out that 41 you can follow along through example 7 in your book. The only difference is that in example 7 the initial speed is a positive 48. V of 0 is 48, while in number 41, since the ball is just dropped, or the stone is just dropped, the initial speed V of 0 is just 0. So you replace, instead of 48, it's 0. Okay, and finally I want to say just a couple of things about number 50, in which we are told that a car slams on the brakes. It's traveling, well, we don't know how fast it's going. It has a constant deceleration of 16 feet per second when it hits the brakes, and it produces skid marks of 200 feet before coming to a stop. How fast was the car traveling when the brakes were first applied? So what we want to find is this v of 0, or what's normally called v sub 0, which is our initial velocity. So we want to find how fast the car was going when time t equals 0. So what we're told is that, our acceleration is negative 16 because we hit the brakes and we're decelerating, so a negative 16 feet per second squared. is our acceleration. So that means that our velocity, which is the antiderivative of acceleration, is going to be negative 16t plus some constant. Now, what is that constant equal to? Well, if I put 0 in for t, I get negative 16 times 0 plus c, which is equal to my initial velocity, which we're going to call, again, v sub 0. So I'm going to replace the c with v sub 0, and you can always do that. Your velocity is going to be your antiderivative of the acceleration plus the initial velocity. Well, I shouldn't say always, but in this case it's going to be just that, negative 16t plus v sub 0. So now when is the velocity 0? When v of t equals 0, we have negative 16t plus v naught equal to 0. So what does that mean? That means the time is going to be, well, negative v naught over negative 16, or just the initial velocity over 16. In other words, the problem with this problem is that we don't know the initial velocity. That's what we're trying to find, this v sub 0 here. But what we do know is that when the velocity is equal to 0, we can solve for t and say it's going to be whatever the initial velocity was divided by 16. This is all because of the fact we know our initial deceleration was negative, or initial acceleration function was negative 16 feet per second per second. Alright, so let's go ahead and work off of that velocity function, v of t, to get our position function, s of t. So let's do that right here. S of t is going to be the antiderivative of the velocity function, which is negative 16t squared over 2, remember, because the power on our variable t there is 1, plus some constant v naught. The antiderivative of that is going to be v naught times t, plus some other constant to get the most general antiderivative, which, which, based on the information in the problem, if we let 0 be the place where the car hit the brakes, the position 0, then we can just use 0 for this constant for the antiderivative for our position function. So s of t then is just going to be negative 16t squared over 2 plus v naught t, or just negative 8t squared plus v naught t. Now, what do we know? We know that when s of, alright, so at time t equals v naught over 16, remember that's when the velocity function v of t is equal to 0. T is equal to v naught over 16. So we know that s of that value, s of v naught over 16, has to equal 200, because the car went 200 feet. Remember, s is our position function. Let me rewrite the argument there of our position function. S of v naught over 16 equals 200. So if you put v naught over 16 in for t, what you're going to be basically left with in your position function is v naught. So you want to solve this equation right here for v naught to find your initial speed. That's what you're going to want to do. So that's it for 4.9, which means that's it for chapter 4. Your password for the homework, peregrine. P-E-R-E-G-R-I-N-E. Peregrine, which is very appropriate for this lecture because it describes what I did. It means having a tendency to wander, as in wander around aimlessly. P-E-R-E-G-R-I-N-E is your password for 4.9. Good luck, and as always, please let me know if you have any questions.